Okay, so yeah, I'm ready. So what we can do is okay. So our topic was modeling with. Okay, maybe I choose some other color. Okay, modeling with second order ordinary differential equations. It means that the applications. Okay, applications. So there are three main situations. Mass spring system. So two are about the mass spring systems. And here we have talked about the free oscillations, okay? And then the second one was also the mass spring system. And then that was the damped oscillations, damped oscillations. And the third one was mass spring system also. And then this is the forced oscillations, okay? Forced with damped or free, whatever, okay? Forced oscillations. And the fourth application was the RLC circuits, okay? So I have uploaded all the videos about these applications over here. I just now want to explain, provide some explanation a little bit. So for example, you have a spring. If you have a spring over here, and then there is a mass which is hanging on the spring, okay? So that mass will have a weight, and then that weight will push the spring down. So it means that if you hang a mass with the weight W, and that weight W will push the spring down by some distance S0, okay? So the force in the spring will be, in that case, will be equal to K times S0, okay? K times S0 in the upward direction. And the downward force will be the W, which will be the weight, okay? So S0 is the distance, and the force in the spring will be the K times S0. And the force in the spring comes from the Hooke's law for the springs. Okay, so in this case, when there is an external force, okay, when there is an external force which is downwards, and when in that case, if for example, is if this mass is brought to some other location, so for example, here. No, sorry, again, is here, further a distance down by y, okay, from its equilibrium position. So this is the equilibrium position, this one. This level is the equilibrium. So further distance down, it is brought down, and then it is released. So at that time, the mass is in motion. So here the mass is in motion, okay? And then there is an upward force on that as well, and then there is a downward force as well. So downward force is the weight. Upward force will be, in this case, will be equal to the total extension in this spring, okay? K times S0 plus Y, okay? Total extension in the spring. So in the first situation, when in this case, when the mass was in at rest, okay, the mass was at rest. So we have two forces. Downward force was W, which we can represent it by mass times the acceleration due to gravity. And remember that we take the sign convention as given in this book as the downward force or the downward motion is represented by a positive sign, and the upward force is represented by a negative sign, okay? So you must remember this sign convention, okay? Sign convention. So in this situation over here, when the mass is at rest, so the downward force is mg and the upward force is ks naught. Okay, ks naught. And since due to the sign convention, we will represent by minus ks naught. And their resultant will be 0 because mass is at rest. There is no net force on this. Okay, so from this relationship, we found that mg is equal to ks naught. Okay. In the second case, when the mass is in motion, okay. So for example, this mass was pushed a distance y downward, and then it was released, and then the mass will start moving in the oscillatory fashion. So in this case, there will be a resultant force. Okay, so what are the forces over here? Downward force is W, which is same as mg. And the upward force is K times S naught plus Y. And from our sign convention, it will be minus K times S naught plus Y. Okay, S naught plus Y is the total extension in the spring. So now there will be a resultant force because the mass is in motion. So that resultant force will be equal to the, since it is in a motion, so according to the Newton's second law, it will be the mass times the acceleration. Okay, acceleration. Newton's second law, mass times the acceleration. So in this case, we can now simplify this equation. So mg minus ks naught minus ky is equal to ma, whereas a is the acceleration, and acceleration is actually the second derivative of the displacement. Okay, if you take the displacement as y of t, its prime, y prime of t will be the velocity. Okay, velocity of t, and the second derivative of y, or the first derivative of velocity, will be called as the acceleration. So acceleration is basically the second derivative of the displacement. So we will represent it by my prime. So now this term mg minus ks naught is 0 as from this equation. So the only two terms left, my prime plus ky is equal to 0. So this is the differential equation. This is the differential equation for this case. Okay, mass spring system, free oscillation. Okay, mass spring systems, free oscillation. So this is how we derive the differential equation for the free oscillation. In the case of mass spring system with the damped oscillation, so there is a damping force. Remember that this type of free oscillation situation is a highly hypothetical situation. In all practical situations, any type of spring will have some effect which will try to resist this motion. So that is that internal effect will be called as the damping of the spring. So this damping can be internal from the spring, or this damping can also be provided by immersing this spring into some immersive medium such as water, or such as some viscous liquid, etc., to provide the damping. So now in the second case, then we can provide a damping force. Okay, damping force. So how we can represent the damping force? So the damping force, it has been found that the damping force is proportional to the velocity of the motion. Okay, proportional to the velocity of the motion. So the more this spring moves, the faster the spring moves upward and downward, more will be the damping motion. So the velocity we represent by y prime over here. Okay, so it is proportional to, so that damping force is proportional to the velocity. So maybe you can represent as damping force. Okay, damping force is proportional to the velocity. So since it is proportional to the velocity, so it will be y prime times some constant. So this constant is called as the damping constant. So by the same approach, okay, so we can introduce a damping constant over here. okay, as well. So for example, initially, if we take that the downward in this damping force force case, if we take that the initially there will be a weight mg, okay, there will be a weight mg in the downward direction, so that will be positive, and the spring force will be the k times s naught plus y, k times s naught plus y, and the damping force will be minus cy, because damping force is also resisting the motion. So therefore, if we are considering the downward motion, so the damping force will be in the opposite direction. So it will be represented by minus cy prime. And the resultant force is m times the acceleration. So by the same approach, so we can get the equation from here. It's like my double prime plus cy prime plus k y is equal to 0. So this is the equation for the damped free oscillations. Okay, so this is the damped free oscillation, and this is the undamped free oscillation. Okay, undamped free oscillation. Remember that in your book there is of course a lot of other derivations as well, but you can follow along those derivations, but you don't have to remember any formula from these derivations. It is not necessary. Only thing is this type of understanding. Okay, the only thing which maybe we need to know is that this k is this constant k, and then the ratio k over m is represented by this, okay, over here. Omega naught is equal to k over m. So for example, if we take this equation, or maybe first equation, any of these equation, we will get a ratio over here as k over m. Okay, so this ratio k over m, square root of that is represented by omega naught. Omega naught we use in the solution, because omega naught actually represents the time period. Okay, so for example, time period of the motion, because since it is an oscillatory motion, that means the spring moves up or down, up or down. So it's an oscillatory motion, so it will have a time period. So that time period is actually represented by omega naught. More precisely, this time period omega naught is equal to 2 pi over omega naught. Sorry, the time period t is equal to 2 pi over omega naught. Okay. The only thing which you may need to remember in addition to that, maybe something like this. Okay. Otherwise, the very complex formulations over here are just for the derivation purposes. Only if you remember this basic concept, how the equations are derived, then you can solve any type of problem over here.
Excuse me, may I ask?
Yes.
So in this second order differential equation, C is omega naught, right?
C is not omega naught. Omega naught is square root of k over m. C is the damping constant. Okay.
So it will be given, right?
Yes, it will be given. It will be there. It will be provided in this statement of the problem. Okay.
Okay, thank you.
C is the omega naught. So only thing which we need to understand is this omega naught is equal to k over m. So omega, this will be the natural. This will represent the natural time period or natural frequency. If it is the time period is represented by this, so the frequency will be f naught will be represented by 1 over t. So it will be omega naught over t pi. That will be the frequency. So This will be the thing. And yes, and yes. So for these equations, very often you will get the solution in this type of format. Okay. Especially when the roots of the characteristic equations will be the complex conjugate. So you will get the roots of this equation, you will get the solution in this type of format in many cases. Okay, if you get the solution in this type of format, so for example, A times cosine omega naught t plus B times sine omega naught t. Okay, in this case, if you get the solution in this type of format, then you can also represent this solution in this type of format as well. Y is equal to C times cosine omega naught t minus delta. Okay, where C will be equal to square root of a square plus b square, and tangent of delta will be equal to b over a. Both representations, this one and this one, are same numerically, both are same, and then we can prove that this representation is the same as this representation. And in fact, I have proved it in my recorded video as well, so you can look at here. But sometimes choosing this type of representation may be more convenient. Okay, so once you find the equation in this format, you can convert it into the other format, and then that will be more convenient for our understanding. Okay, so that were those were the two cases. Any questions about that?
No question.
Okay, up to now, no question. Okay, so now let's look at the forced oscillations. Okay, forced oscillations with or without damping. Yeah. So in the forced oscillation, what is the difference over here? Because in the free oscillations there is no external force which is driving these springs. Okay, we are not considered. So we just take a mass which we hang from the spring, and then we initially move that mass to some position and then let it oscillate freely, but we don't consider any force. So if we consider any force over here, so in this case this will be the mass, okay, and this will be the weight, and this will be the additional driving force. Okay, you can represent it by D, and then there will be the spring force in the spring, okay, which is represented by a force in the spring, which is represented by K into S naught plus Y, and this is represented by mg. So these are the forces acting. So, and then another the damping force, which will be the C times Y prime. Okay, so if we so this is the system in motion. Okay, system in motion. So and the downward is positive, upward is negative. Always remember about this type of notation. Okay, so in this case, how we can represent these forces? So mg is a downward force, weight, minus ks naught plus y is an upward force, minus cy prime is an upward force, and the driving force, we suppose that it is a downward force. Okay, so this is the driving force. Okay, down, and then the resultant of this will be equal to the mass times the acceleration, which is basically equal to my prime. So since we know that mg minus ks naught is 0, so mg and ks naught cancel out. So we get this equation, my prime plus cy, my double prime plus cy prime plus k y is equal to this driving force. So this is the equation we get. So compared with the previous equation over here, this is a same equation but with a non-homogeneous term. So this is a non-homogeneous equation. Okay, so normally speaking, it is only practical. It is more practical to represent this driving force in terms of a sine or cosine function. So for example, if we take this driving force as equal to cosine of omega t, okay? Now, why we have to take this cosine function as over here? Because if we have this f naught times cos cosine of omega t, so for some values this force will be plus, or for some values this force will be negative, because depending on the values of the cosine of omega t, the values will oscillate from plus or minus, or it means that the direction of the force will be sometimes downward, direction of the force will sometimes be upward. Okay, so this is the more practical case. So it may be some type of a piston which may be driving upward or downward or these kind of things. So this type of representation of the driving force, f naught cosine of omega t, is more representative for this oscillatory motion. Okay, so we represent this fd by the f naught cosine of omega t. So simply speaking, this is another equation which we have no problem with that. We have already seen this type of equation for the non-homogeneous equation with the constant coefficients. Okay, so we can solve this equation analytically by any given values over here. The only thing is for us to understand the different coefficients. So what is a mass? Okay, what is a damping force, and what is a spring constant, etc. So then we can apply this equation, and then we can solve the questions. So there are of course some other formulations which are given in the book, but we don't have to memorize those formulations. The only thing which over here is maybe you can understand is that the resonance phenomena. So what is the resonance phenomena? Remember that I have represented over here this driving force by cosine of omega t, but here we have used a term m over k, which was equal to omega naught. Okay, so in this case, when we can compare omega naught and omega. So both represent the both are some sort of representations of the frequencies. So omega naught is the natural frequency. Okay, it is the natural. Omega naught represents. Okay, actually it's the formula is for 2 pi over omega naught. Omega naught over 2 pi. So omega naught represents the natural situation. Okay, natural time period. Okay, natural frequency. Okay, frequency of system. So this is inherent to the system. It depends upon the material of the system. Okay, whereas the omega is the driving frequency. Omega is the driving frequency for the external force. So when omega and omega naught are quite close to each other, or they match with each other, so then a phenomena occurs which is called as the resonance. Okay, in this resonance, then eventually the amplitude of the motion becomes bigger and bigger. So we can get a curve something like this. Okay, in the case of resonance, so the amplitude of the motions becomes bigger and bigger. So this type of phenomena we can observe. Okay, when the the frequency of the driving force is matching with the natural frequency of the system. Okay, so although there are some formulations given in the book, but I don't recommend to memorize those formulations. Just use the basic concept of these equations, and then we are good. Okay, so any questions about that?
No.
No, okay. Okay, next we can talk about something about, for example, if instead of there is a one spring, you have been said that there are two springs, okay, and then there is a mass hanging with mass hanging with these two springs, okay, so K1 and K2. So here you can have uh, K1 and K2, okay, and the mass is hanging to these springs. So in this case, how we will use the value of K into these equations. So for example, let's take these simple ones, my prime plus Ky is equal to 0. For example, if this is the free oscillation system. So what value of K we will use in this case? When the two springs are parallel with each other. So in this case, we will use the value of K, which will be the resultant of these two K values. Okay. So in this case, the effective spring constant will be equal to the sum of these two values. Okay. This we can prove by, for example, in this case, the force provided by these springs will be equal to this force provided by spring K1 and then this force provided by spring K2. If we add up these two forces and then replace it with the single spring with the effective strength, so we can easily get this type of effective spring constant. Okay. So in this case, the value of K which you will use into this equation will be equal to K1 plus K2. Okay. Another situation can arise in which case, in that, for example, if you have a spring over here with the spring constant K1, and then there will be another spring which is hanging with the first spring with the spring constant of K2, and then there will be a mass hanging with that. So in this case, what will be the effective spring constant? So it has been found that the effective spring constant, and then it can be also derived that effective spring constant will be equal to K1, K2 over K1 plus K2. I will not make the derivation over here, but you can very easily, by considering that in this case, the difference is that this displacement in spring K1 plus the displacement in spring K2 will be equal to the total displacement for the effective spring. Okay. So if we can represent it with the another spring with the resultant of the two spring constants, K effective. So the total displacement of K effective will be equal to the total displacement of K1 plus K2. But the force in both springs K1 and K2 and K effective will be same. By considering these conditions, we can derive that K effective in this case will be equal to K1, K2 plus over K1 plus K2. Okay, so this thing you can remember. So for example, if you have some questions in which instead of just one spring, two springs are given in parallel, okay, like this parallel springs. So how we will find the effective K? So then you will just add up those. Or if the springs are given in series, so series springs. So how we will find it? So you can find the effective springs like this. Okay. Is it clear?
Yes.
Yeah.
Okay, so with that the spring part is okay. Then let's talk about the RLC circuit. Okay, RLC circuit or LRC circuit. RLC circuits. So this is something which is related with the electrical engineering course, but nevertheless we can represent it. So R is for the resistance, L is for the inductance, C is for the capacitance. So the real meaning of these terms, inductance, capacitance, etc., is more familiar with the electrical engineers. But what we can say is over here is that the circuit is like this. So here it is a capacitor, and here we have an inductor. Inductor is represented by this, and here we have a resistor. Okay, and then this is driven by an electromotive force. Okay, so it is represented by E of T, electromotive force. So this equation depends on the Kirchhoff's voltage law. Okay, so which says that the drop of voltage across the resistor, capacitor, and inductor in a circuit is equal to the sum of the voltages across individually these components. So for example, the voltage drop across the resistor is plus the voltage drop across the capacitor, and plus the voltage drop across the inductor is equal to the total electromotive force. So this is simply the Kirchhoff's voltage law. So in this case, the voltages of VR, VC, and VL can be represented by different expressions. So for example, voltage across the resistor is represented by the current across the current passing through the circuit and times the resistance. The voltage across the capacitor is represented by the charge through the capacitor divided by the capacitance. Okay, divided by the capacitance. And the voltage across the inductor is represented by the inductance, okay, multiplied by the multiplied by the sorry, it is current, okay, the change in current, okay. Just a moment, I need to check my notes if whether I'm not making any mistake or not. Yes, yeah, di over dt. Yeah, L is equal to di over dt or I prime. Okay, change in current with respect to time. So then we can input these values over here. VR is equal to I times R, plus VC is equal to Q over C, plus VL is equal to L times I prime, and equal to the ET. ET. So in the end, this type of equation then can be represented by Li double prime plus Ri prime and plus I over C, okay, is equal to the electromotive force. Electromotive force. This is also represented by some other constant E naught times cosine of omega t. So this is, mathematically speaking, this is the same equation as was for the forced vibrations in the mass spring system. So we can use the same equation, similar equation like this. So in this case, the L has a analogy. L has an analogy for a mass, okay, and R has an analogy as a damping force, C, sorry, small c, damping force, small c. And the K, the spring constant, has an analogy with the 1 over the, the opposite, okay. 1 over C, that is the capacity, the inverse of the reciprocal of the capacitance has an analogy with the spring constant. So you can see that we can analogically we can represent the mechanical and electrical systems with each other. Okay, and this type of concept can be useful for representing a mechanical system which may be difficult to make, to represent by some electrical system which may be rather easy to make. But anyway, mathematically both equations, forced vibrations and the RLC circuits, are the same. So in fact, I have uploaded the video about that as well, and then you can have a look. And there is one example which I have also solved about that video. Okay. So with this, I will, the topic of the second order ordinary differential equation is completed. So if you, and then later on, I will also upload some of the practice problems about the applications of this second order differential equations. That means the modeling with the second order differential equation. So now everything has been covered about this topic. As far as your textbook is concerned, even some more material has already been provided to you as well. So do you have any questions?
No questions. It's more likely that final will be 50%, yes?
Yeah, I will confirm tomorrow after the meeting with the other instructors. Okay. So yeah, because the other sections have also 50%, so it's more likely. Yeah, I can say as of now. Do you have any more questions? Okay, so after that we will start a topic which will be the Laplace transforms. Laplace transforms. Okay, Laplace transforms. This is actually chapter 6 of your textbook. Okay, so from chapter 1 and 2 we are jumping towards the chapter 6. Okay, this is also a very interesting topic. So in the Laplace transform, what you do is basically, this is also a method primarily for solving the differential equations. Okay, this is a method for solving the differential equations, but the approach is different. So in this case, you transform a differential equation into an algebraic equation. Okay. Okay, you can transform a differential equation into an algebraic equation, and then that algebraic equation, then, because you know that the solution of the differential equation is a function in the algebraic format. So you transfer the differential equation into the algebraic equation, and that algebraic equation will give to the solution, okay, of the differential equation. So this is the process. So therefore, there is no need to apply those differential equation methods which you learned in chapter 1 and chapter 2. You can learn a new method for the solution of the differential equations. So this type of approach has actually some advantages. Normally, if you see that in the differential equations, you first determine the general solution. Okay. So for example, if there is an initial value problem, so you first find the general solution, and then you find the solution of the initial value problem. Okay. So this is in the normal, this is the normal method. Okay. Normal approach. However, in the Laplace transformation approach, you don't have to find the general solution. You can directly find the initial solution of the initial value problem. Okay, so this is one type of This is one advantage of this method. Similarly, in this method, the advantage is that in the case of the second order equations, so equations, so we first find the YH, the solution of the homogeneous part, and then you find the YP, the solution of the particular part. But in this approach, in the Laplace transform, you can directly find the solution. Okay, there is no need to find for homogeneous and particular part. Okay, so in this way, this method gives us some advantages. That means maybe the calculations involved are much less than the in the normal methods. Okay. However, this solution, this type of method, also has some disadvantages, because sometimes when you find this algebraic equation, to convert that algebraic equation to this final solution, it becomes sometimes quite challenging. Okay, it becomes sometimes quite challenging. So in this type of approach, is also especially useful for discontinuous functions. Okay, discontinuous functions. So this type of approach is especially useful. That means the Laplace transform. Okay, so we will learn about the functions such as the Heaviside function, and Dirac delta function. So the normal methods for discontinuous functions do not work very well, but especially this type of method using the Heaviside function, which we will describe later on, and the Dirac delta function, which we will also describe later on. This method works very well. Okay. And also, this method uses some tables. Okay. Okay, uses some tables. So you just have to see the Laplace transform from the table, and then you can directly apply that Laplace transform. You don't have to derive Laplace transforms of functions. No, there is not required. Okay. So for the basic functions, the Laplace transforms have already been derived. So we just have to use those Laplace transforms from the table, and then transfer them back into our final function for the answers. So the tables are available in the book. So for example, a shorter table is available in the first part of the first section of this chapter 6, and a slightly longer version is available at the end of the chapter. And if you need some more comprehensive tables, then of course elsewhere we can also find those tables as well. But basically, the table which is given on in the first section of the book, that will be sufficient for our purposes. Okay. So this was the brief introduction of the Laplace transforms, which will be our next topic. So I will shortly upload the lecture handouts for that transform, and then I would also try to record some videos about this function. Okay, so do you have any questions?
No.
No. Think about it. Think about any questions if you have in the next 3 minutes. Yeah, I can see that the participation in this class is very low. Just 22 of them are here, which is not good. Well, I should say this to those who are not present over here. Those who are present, they are okay. They are very good. They are very enthusiastic with this course. But those who are not present, I am not impressed with them. I am very much unhappy about who are not present. From a class of 52, there are only 21 present. So this is not good, actually. So I will soon give a reminder on the email. All right, so I wait for your questions within the next 2 minutes, and then I can finish this meeting.